Hello, today we're going to talk about the Haber process. The members of the team are Marian Chavez, Sofia Archundia, Porfirio Preciado, and Diego Delgado. In general, the Haber process combines nitrogen from the air with hydrogen, derived mainly from natural gas, into ammonia. The history of this process began more than 175 years ago, when there was a scientific debate raging in Europe over the importance of nitrogen for the growth of plants. The solution soon came from the German scientist Fritz Haber, who discovered the process in 1909, that the chemical reaction of nitrogen and hydrogen produced ammonia was the mainly component in nitrogen-based fertilizers of. In July of the same year, Germany's largest chemical company, BASF, founded by German chemist and engineer Karl Bosch, developed in commercial scale the production of ammonia. This process wasn't easy, however. Ammonia production depended on high temperatures and pressures, as discovered by Haber. Much of the necessary machinery had to be invented to handle the extreme production conditions. Bosch's machine, unveiled in 1914, stood 26 feet tall and produced 198 pounds of ammonia per hour. Later, Haber's and Bosch's contributions to ammonia production were honored with two Nobel Prizes. Haber was presented with a Nobel Prize in 1920 for his research that unlocked the ammonia production process, and in 1932 Bosch and Frederick Bergius received the Nobel Prize for their contributions to the invention and development of chemical high-pressure modern methods. Today, a modern ammonia production facility produces approximately 1,000 tons of ammonia per day.
Haber process is the industrial production of ammonia using nitrogen and hydrogen at 450 Celsius degrees and a pressure of 200 atmosphere using iron as a catalyst. This is one of the most important reactions of the world because thanks to the ammonia we have nitrogen-based fertilizers which allows to grow most of the food we eat today. In order to make this reaction, as I said, we need nitrogen and hydrogen. The nitrogen is easy to get given that 78% of the atmosphere is nitrogen. However, hydrogen is more complicated to acquire. We need to subtract it from hydrocarbons such as methane. There are two important things we have to note about the reaction. The first one is that it produces heat. So that means it's an exothermic reaction. And the second one is that it has two-way reaction manner, which means that it's reversible, and some of the ammonia will break back down into hydrogen and nitrogen again at certain properties.
The first step in the process is to take the hydrogen and nitrogen layer using as a reactant and feed them into the top left of the machine where they can mix together. In the first part, the reaction in a vessel where the conditioner keep at 450 degrees Celsius and 200 atmospheres, and the gases are free to pass over this iron catalyst. Under these conditions, the reactants form ammonia. This is an important part because we have a reversible reaction. The mixture will still contain lots of nitrogen and hydrogen. This means that we need to somehow separate the ammonia that's been formed from the nitrogen and hydrogen that haven't reacted. Ammonia has a fairly low boiling point, and so by passing the entire mixture through this pipe into the condenser, which is colder than the reaction vessel, we can cool down the gaseous ammonia until it condenses into liquid ammonia, whereas the gaseous nitrogen encases hydrogen will stay gaseous because they have higher boiling points and they can be recycled back around into the reactant mixture. In this process, our iron is used as a catalyst because it makes the hydrogen and nitrogen molecules unite to its surface. This reaction weakens the covalent bonds and finally causes the dissociation of the molecules.
In order to understand why such conditions like 400 degrees and 200 atmosphere, we have to keep in mind three basic things in every reaction: the percentage of yield, the rate of reaction, and the cost. Because it's an exothermic reaction, we're going to need a lower temperature in order to favor the forward reaction and obtain a higher percentage of yield. Although, in order to achieve a high rate of reaction, we need a higher temperature, because the particles need a big amount of kinetic energy to react. Finally, generating heat is expensive, and that's why we use a temperature that is not so high but not so slow, and that is 450 degrees. In words of pressure, in order to achieve a higher percentage of yield, we need a higher pressure, because there are fewer molecules of products than there are of reactants. So a higher pressure will favor the equilibrium to the right. We also need a pressure to obtain a high rate of reaction, because the particles collide more frequently. However, the only thing limiting how high the pressure could be is the cost. Maintaining a higher pressure is very expensive, and it's also dangerous. That's the reason why 200 atmosphere turns out to be the best pressure.
Ammonia is used to produce fertilizers, nitric acid, and certain household cleaning products. Fertilizers are used to increase the nitrogen content of soil, or in other words, make it more fertile. Nitric acid is used in the production of ammonium nitrate and other nitrate-based fertilizers. It's also used as starting material for many explosives, and also is very important for the pharmaceutical industry. It's used to produce certain dyes for food coloring in the textile industry, and even as an indicator. In the laboratory, it's used to clean glassware, but a much interesting application is used in the purification of gold and platinum.
In conclusion, while researching the Haber process, we were able to realize its importance and how chemical engineering can carry out a reaction from the laboratory to an industrial scale. Something that also made us see was how we can apply everything we have learned in that course and in the past courses during the career. For example, chemical kinetics, how the rate of the reaction depends on the temperature and concentration of the products, about how chemical equilibrium occurs in a reaction. As we said before, it is an exothermic reaction because delta H is equal to minus 92.6 kJ per mole. So here we see that the principle of Le Chatelier is fulfilled. In this case, the rate of the reaction is very slow under normal conditions. So that's why we must change the temperature and pressure to obtain ammonia. But always being careful not to increase the temperature so much, because if not, the reaction returns to the reactants. You can also see what was seen in the class about partial pressures and total pressure according to Dalton's law. Finally, we can finish by saying that it is a simple reaction, but very important and useful. One of the best discoveries.
Well, and that will be it. Thank you for your time, and see you in the next one.